Hello everyone, I'm Gianluca Brilli from the University of Modena Reggio Emilia. Today I'll present architectural design exploration of a lane detection vision pipeline for FPGA-based F110 autonomous vehicles, funded by Shape Future European project. Lane detection is the process of identifying lanes on a road using image processing techniques like computer vision or deep learning. And lane detection plays a crucial role in the field of autonomous driving, since it can be used as a lane keeper, for example, or to detect lane changes. The lane detection can also be used as a component of a more complex perception system. Autonomous cars are composed of several tasks like perception, localization, mapping, and others, which are deployed on the same hardware chip. A computer vision-based lane detection system can be designed as a pipeline of computer vision tasks, like the one that is reported in this slide, that we used as a baseline. This is a C++ implementation from the repository below. It takes as input a frame retrieved from a camera and provides an output frame containing the detected lanes and the turn prediction that can be right or left. The first step is the image denoising, that applying a Gaussian filter removes the undesired pixels from the image and improves the lane detection accuracy. The second step is the edge detection, that in turn is composed of three different phases that are BGR to gray transformation, a threshold function, and a filter 2D. And the purpose of this phase is to get the boundaries of the lanes. Then we have a mask phase where only the edges that fall inside our region of interest are considered, and of course our region of interest is the road only. Then, using outlines detections, the location of the lines of the road are reported to the initial input frame, as reported in this figure. Finally, using a sequence of linear algebra transformations and regression, the algorithm takes a decision to turn left, right, or keep going straight. The target system of our work is the F110 platform, that is an open research platform to evaluate autonomous driving algorithm using a 1/10 scale autonomous car. The car is equipped with different sensors and actuators, like a stereo camera that we used as the input sensor for our lane detection system, and a LiDAR, which is the main sensor used to drive autonomously. Then, as a main onboard computer, we used the AMD Cria KV, which is an industrial-grade heterogeneous system that is composed of a multi-core processor and an FPGA logic. We adopted Cria to deploy our computer vision-based lane detection system, and we used the Cria as target since it has a small form factor to fit inside an F110 car and a limited power consumption. But the Cria also has limited hardware resources, and hardware acceleration is needed. Our goal is to explore a vision-based lane detection system as part of the perception stack that we already have on our F110, and to explore hardware acceleration for the lane detection system. However, using HDL to design accelerators is complex and time-consuming, so we adopted HLS to implement our computer vision kernels using VTIS Vision, that is a library from AMD for optimized computer vision kernels. We also adopted overlays architecture to simplify deployment of accelerators and interactions between CPU and accelerators. Of course, we released hardware and software open source. After a software profiling of the 7 kernels, we decided to accelerate the first 3 kernels using the FPGA, while the other 4 kernels are still deployed in software on top of the host processor. For the three kernels, we adopted the AMD with its Vision library, while the software components are implemented in C++ using the OpenCV library. In the next part of the presentation, I'll discuss our architectural design exploration that is composed of three different architectural optimizations. In the first one, we evaluate the impact of using local memories inside the FPGA to improve data locality and to reduce memory transactions involving the main memory. And the local memory is implemented on top of the Crea FPGA using block RAMs. In the second architecture, we deployed a small soft core implemented in FPGA that we used as a local orchestrator. The soft core is closer to the FPGA accelerators and it can access accelerator register quickly compared to the host CPU, since we have a closer path to the register files, less interconnections, and lightweight hardware links, like for example Axis Stream. In the third architectural implementation, we used the previous local core and local memory, but we evaluated the impact of using a pipelined execution model respect to the sequential used with the previous setups, where all the kernels are executed one after another in a strictly sequential manner. Following this model, all the kernels are executed at the same time and organized in stages. At each stage, every accelerator processes their data in parallel, while data for the next iteration is fetched using a double buffering scheme. In the final part of the presentation, I'll analyze the results achieved with the previous architectural templates plus the final analysis of the area utilization. For the experiments, we report bar graphs that represent the speed up achieved with respect to the baseline, which is the software implementation implemented in C++ using OpenCV. On the x-axis, we have the kernels, the accelerated kernels, while on the y-axis, we have the speed up that we achieved. In the first experiment, we report the speed up achieved using global shared memory, the DRAM, while all the kernels are controlled remotely using the ARM CPU, that is the host processor. Here we can notice that Gaussian filter and filter 2D are the kernels that benefits the most compared to the others, achieving a 92 times and 7.5 times of speed up compared to the software execution. Then the total speed up of the application, considering also software kernels, is 2.1 times, while the average speed up of the accelerator kernels is 15.7 times. Here the orange bars represent the second architectural template, where all the kernels access a local shared memory inside the FPGA that is implemented using block RAM. Here we can notice an improvement, especially for the mask kernel, where its speed up is almost doubled, from 2.6 to 5 times. The accelerators that are memory bound gain the most from this optimization, compared to the kernels that are more compute intensive. The last hardware template that we consider is the local control, where in this case the interactions with the accelerators, in contrast to the previous architecture, are directly managed by the local controller, a core that is closer to the accelerators that uses lightweight hardware links to interact with the accelerators. The experiments are represented with gray bars. From this experiment, we can observe an improvement using a local controller for all the kernels. And here the kernels that benefits the most from a local orchestrator are the kernels that require a high number of parameters and high number of interactions during their execution. For the final experiment that quantifies the improvements using a pipeline execution versus a sequential model, we used the last hardware architecture that was composed using local memories and a local orchestrator, and we implemented a pipeline execution model. Such execution is directly managed by the local orchestrator. In this case, we considered the end-to-end execution of the of the accelerator kernels only, and we finally achieved a 22.3 times of speed up compared to the 16 times of the sequential model. Finally, we report the FPGA utilization of the AMD Cria KB in percentage, and is reported in the figure in this slide, where on the y-axis we have the percentage of utilization respect to the Cria availability of resources, and on the x-axis we have the FPGA resources. The blue bars report the first architectural design with global memory and remote control. The orange bars are the optimized version with both local memories and local orchestrator, while the gray bars represent the utilization of the whole block design of the optimized version. Here we can notice that lookup tables and blockrams are the most used resources on the Cria KV with these implementations. To conclude the talk, I presented how a lane detection system, a component of a more complex perception system for autonomous cars, can be accelerated on FPGA-based heterogeneous system. We evaluated different architectural template and library components, and we achieved a 2.10 times of speed up considering the whole lane detection pipeline using HLS accelerators, and 22 times of average if we consider only the accelerated kernels. Our hardware designs and software implementation are released open source. And as future works, we plan to fully integrate the lane detection component on our F110 autonomous driving stack. And we also plan to accelerate other kernels of the lane detection pipeline. Thank you for your attention, and if you have any questions, you can ask.